what we're doing is a creative process. So we definitely search for those times or those occasions where you can make your code feel a little bit like art.
New frameworks, new standards. Things are changing so fast. You're always learning. That makes me happy.
For me, it was really fascinating when I discovered what programming actually is. When you make up an algorithm in your mind, you could execute it yourself with pen and paper or just by thinking hard. This is truly exciting.
It's really creative. Once you get the hang of it, you can create so many different ideas. It's really impacting the real world.
Every software is an artistic project. Since the first day I saw a line of code, I fell in love with Java programming. It's something on which I love so much.
I'm not sure if I've lost myself in coding or it's who I've always been. Coding definitely is going to get you once you type your first successful LOL. You can do and undo whatever you want, and it makes me want to do more. Obviously, I sleep less, I code more, and I'm delighted when every time my customers say they're happy.
It's a very creative activity. If you ask an artist or a singer, why do you sing, or a musician, why do you write music? For me, I'm an artist, I'm a musician of my profession.
One way of looking at it is that code is another form of communication. With Solid Pi, the goal is to explore the potential for code with music. Can we get anybody, not just musicians, everybody making some kind of crazy beats and sounds by writing simple lines of code?
Once you get your code run, the feeling is awesome. You can achieve anything within your imaginary with coding.
That's why I wanted to code in the first place. Create something brand new that hasn't been seen before.
Having imagination to build something beautiful and efficient, beautiful and usable. It's freedom.
Please welcome George Saab.
Good morning. Welcome to Oracle Code 1. This week, you'll have the opportunity to experience a wide range of technology and, of course, true to our roots, plenty of in-depth Java content. You'll have the chance to hear from Java experts such as Stuart Marks, Poonam Parhar, Jim Manico, Venkat Subramaniam, and many other Java luminaries. Sessions are filling fast, so make sure you've downloaded the Oracle Events app and register for the sessions that you're interested in. We're going to have many more activities throughout the week, and of course, the always popular hallway track where you can meet old friends and make some new ones. Please also check out the Groundbreaker Hub and thank all of our sponsors. Code 1 is all about expanding our horizons and learning new things. Our invited speaker this morning is going to talk with us about a technology that most of us have probably heard of, but maybe not all had a chance to dig into and really understand. She has conducted research at Harvard and MIT, and is currently a Knight Hennessy Scholar at Stanford, specializing in quantum computing. Now, if I were to list all of the awards that she has received, we'd be here all morning. So instead of that, without further ado, please help me welcome Jessica Pointing.
Raise your hand if during your trip here to San Francisco, you have visited Stanford or you intend to go visit it. Okay, more than I expected. Well, if you've ever been to Stanford, you would notice that the campus is pretty large. And so a lot of people ride a bike to get around. And there are some bike sales. And actually, that's where I got this bike. I got this electric bike at a bike sale for just $35. It was a pretty good deal. And as you can see, it's an electric bike. The only problem is it's missing its battery. So it rides just like a normal bike. And one day, I'm riding up a hill on this bike, and a guy sees me, and he assumes that I'm riding an electric bike. And he asks me, how come you're struggling to go up that hill? And I tell him why. But perhaps you have had a similar situation. You've struggled to go up a hill on a bike, and you know it can take you significantly longer to get from point A to point B, your final destination. Well, imagine that computers are like this. We start off with some initial state, point A, and we want to get to some final destination, which can be solving a problem, maybe in machine learning, or in chemistry simulations, or in financial modeling. And the path to get there can be difficult, and it can take our computers a really long time to solve certain types of problems. It could take days or months or even years. Well, quantum computers could change that. A quantum computer is a fundamentally new type of computer that could help us solve certain types of problems significantly faster. You can think of a quantum computer like an electric bike with a battery. It has an extra power, an extra boost that allows us to solve, in particular, difficult problems faster. So this brings up a few interesting questions. One is, what problems could we solve faster with quantum computers? Two is, what is the equivalent of the battery in the quantum computer? We know in an electric bike, the battery gives it its boost, but what exactly gives the quantum computer that advantage? And three, what is the current state of quantum computing? Can you code on one? Can you use one? And we'll explore all of these questions in this talk. So first of all, what problems can we solve faster? Well, because a quantum computer is a fundamentally new type of computer, we actually can't solve all problems faster. We actually have to figure out which problems can we solve faster. And some researchers have already done this. So let's take a look at an example. Let's say I give your computer the number 15, and I say, find me the two numbers you must multiply to give 15. Well, that's extremely easy. Your computer knows 5 and 3 multiply to give 15. But what happens if I give it a 617-digit number? And I say, now find me the two numbers. Well, your computer is not going to be able to handle that. And in fact, it could take up to 1 billion years using the best known algorithms on our current computers to find those two numbers. But what about a quantum computer? And when I say current computers, I refer to them as classical computers. And this is just the term for any computer that is not a quantum computer. So in a classical computer, you could do it in 1 billion years, but what about a quantum computer? How long do you think it could take? And I actually want to see what you guys think. So you can go to this poll at polev.com/quantum225, or you could text, and I want to see what you think. How long do you think you could find those two numbers on a quantum computer? And I'm going to give you a few seconds, and then we'll see what you think. Okay. Ooh, okay, interesting. So you guys know your stuff. So, maybe. So the correct answer is 100 seconds. And that is pretty fast, right? From 1 billion years to just 100 seconds. And this is the power. Now the answers are going down. But this is the power of quantum computers. And how are we able to do this? Well, that's because researchers have created quantum algorithms. Quantum algorithms are a set of instructions that you give to a quantum computer. And Peter Shor, who is actually a professor at MIT, created a quantum algorithm called Shor's algorithm. And using the mathematics of quantum computing, he showed that it could be faster than any of our current classical algorithms to do that problem. Now you may think, okay, multiplying two numbers, is that an important problem? Well, yes. If you're familiar with cryptography and encryption, you know that this is actually what keeps your internet data secure, the fact that it's such a hard problem on our current computers. You can think of those two numbers as the key to a lock. So as long as no one can solve it in 1 billion years, the lock is closed, and your credit card information, your bank information online is secure. But with quantum computers, if you do it in just 100 seconds, you basically have the key to the lock, and you could break a lot of encryption methods. So a lot of people are worrying about this, understandably. But do we need to worry? Well, first of all, in order to do this, you need to have a large quantum computer, an ideal quantum computer. And currently, no one has built that yet. So no one is going and breaking all your encryption methods. But the second thing is that people are coming up with things called post-quantum cryptography. And these will be methods that will be safe against quantum computers. But actually, that's still in its research stage. And you can think, if we need to replace all of our encryption systems, that could take quite a long time. So it is actually an important problem to think about and to start doing work on. But we don't need to completely worry that the internet's going to blow up anytime soon. So we've seen that quantum computing can be applied to security. What about another application? Well, actually, one of the first motivations for quantum computing was to be able to understand nature, to simulate atoms and molecules. And because atoms and molecules, they all follow the laws of quantum physics. Quantum physics describes how the world works at the level of atoms and subatomic particles such as electrons. You can understand its behavior. So it makes sense that we'd want to use a quantum computer, which is a quantum system, to simulate nature, which is also a quantum system. So if we could simulate these molecules and atoms, what sort of applications could that have? Well, one is in medicine. When you want to design new drugs, you want to understand how these molecules interact with the molecules in our body. And so if we could simulate that more accurately on a computer, on a quantum computer, then we could potentially discover new medicines. Well, how about materials? Materials are made up of molecules. So again, if you could understand how these molecules behave and give rise to new properties, then we could potentially design new materials that can make the devices you use, like on your phone, better. So far, we've seen that quantum computing could be applied to security and chemistry simulations or physics simulations. And actually, we know that quantum computers could solve these problems exponentially faster. Now, what exactly does that mean? Well, let's say I give you your phone, and I say, now enter your passcode. But now you only have one digit. Well, that would be completely useless, because you could just solve that in 10 tries. But now, what happens if I add 4 digits? And actually, the iPhone used to be like this. Well, that would actually be harder. Now it would take 10,000 tries. And now you have to enter 6 digits. And the security is even more. Now it takes up to 1 million tries. This is what the problem looks like. Even though the size of the problem increases in a small amount, the time to solve it scales exponentially. And quantum computers, for certain these types of problems, could give us this. You could see that as the size of the problem increases, it doesn't scale for the time to solve it. And that is the power of quantum computing. Now, I can't be at a software conference without mentioning machine learning and AI, but we all know that we've made more progress in AI now because of the more powerful computers we have today compared to many years ago. And in a similar way, people think that quantum computers could also help advance artificial intelligence, and we could apply it to machine learning. And actually, if you look under the hood of machine learning and quantum computing, it's very similar. Machine learning, the mathematics of it all, is a bunch of vectors and matrices. And actually, quantum computing is also a bunch of vectors and matrices. So you can actually naturally map the two together. And this is a field called quantum machine learning, and a lot of people are doing this. Another application is called unstructured search. And to illustrate this, I have a bag with 100 balls. Now let's say I ask your computer, find me the ball number 3 in this unstructured bag of balls. Well, what does your computer have to do? Since there's no structure, it has to pick up a ball, check whether it's the number 3, pick up the next one, and continue until it finds the number. So this could take up to 100 tries, because you could pick 3 on your last try. But what about a quantum computer? How long do you think it could take on a quantum computer? It could actually take just 8 tries. And again, we can do this using a quantum algorithm. And we can generalize it. So on a classical computer, it would take up to n tries. But on a quantum computer, it would take up to square root of n tries. And this is using a quantum algorithm called Grover's algorithm. And later in this talk, we'll see actually how you can implement this algorithm on a quantum computer. So we've seen some really interesting applications: factoring, simulations, machine learning, and search. And these are so general or broad enough that they could be applied to industries. such as artificial intelligence, medicine, materials. And people are even trying to do it more to other industries, such as finance, space, logistics, and scheduling. So as you can see, quantum computing has all of these potential applications. In summary, we could solve the unsolved problems. Something that could take 1 billion years, we could solve in just seconds. And that's what's exciting. So now you may ask, okay, so how are we able to do this? What is the equivalent of the battery in the quantum computer that gives it the boost to solve these problems faster? Well, the short answer is quantum physics. And as I said, this describes how atoms and subatomic particles such as electrons, how they behave. And there are many quantum effects. And we'll focus on one of them in this talk today, called superposition. So what exactly is superposition, and why does that give you a boost? Well, to understand that, let's understand how computers work. We know that computers, they have bits, zeros and ones, and any character can be represented as a sequence of bits. So here, to illustrate this, I have a donut. And let's say the plain side is equivalent to 0, and the frosted side is equivalent to 1. So what about a quantum bit? What would that look like? Well, when a quantum bit is in superposition, it can actually be 0 and 1. It could be a combination of 0 and 1. And you can think of it like a spinning donut. If I ask you, is it 0 or 1? You can't tell. So why does that give us the power? Well, let's say I give you a box, and there are 2 donuts inside. And you open up the box, and I ask you, what combination do you see? Either you'll see 0, 0, which is equivalent to 0, 0, 0, 1, 1, 0, or you'll see 1, 1. But now, if you open up the box, and there are 2 quantum bits spinning, you say, well, I see all of the combinations at the same time. And that is the power of quantum computing. You can actually be in multiple combinations, multiple states at the same time. And what power does that give us? Well, that means that when we're doing the computation, we can process these multiple states of bits simultaneously. And so now I have another question for you. How many combinations will there be if you had 300 qubits in superposition? Let's see what you guys think. Okay, interesting. All right, so the answer is 10 to the power of 90. So why is that? Now the answer is go. But actually, 10 to the power of 90 is an insane number. That's 1 with 90 zeros after it. That's more than the number of atoms there are in the observable universe. And why was it 10 to the power of 90? Well, as I said, if you have n qubits, you can be in 2 to the power of n states. So 2 to the power of 300 is roughly 10 to the power of 90. So this is the power of quantum computing. Now you may ask, so how does it actually work? How does a quantum computer operate? Well, let's understand how a normal computer operates. On a normal computer, you have logic gates. You have a 0, you put it through a NOT gate, you end up getting 1. And then we combine these logic gates to make modules, to make chips, circuits, and then you have your computer. Very simplified. Well, in a quantum computer, we have similar things. Instead of logic gates, we call them quantum gates. So we actually have the equivalent of a NOT gate. It's called the X gate. So this says if you have your bit and you put it through the X gate, it ends up flipping it over. Okay, well that's fairly simple. That's what a classical computer can do. But we have another gate called the Hadamard gate. Now this gate puts our qubit into superposition. So it's 0, and then when we put it through the Hadamard gate, it now ends up spinning. And this is one of the powerful effects of quantum computing. And we actually have multiple other gates that do other quantum effects. But what the goal is you can now execute a quantum algorithm with these quantum gates. And the goal of the quantum algorithm is to use these quantum effects in special ways to solve the problem. And so when you combine multiple of these quantum gates together, that's how you can get a boost. So actually, let's revisit one of the algorithms we saw. That is the one with the balls, Grover's algorithm. So to simplify the problem, I'm only going to have 4 balls. But let's say again, you want to find the ball number 3. Well, how do we do that? On a classical computer, it could take up to 4 tries, since you have 4 balls. But on a quantum computer, you could actually do it in just 1 try. Why is that? Well, if we want to execute this on a computer, we have to convert it all to bits. So here's the number, and we convert them to bits. And we want to find the bits 1, 1. So this is the quantum circuit for Grover's search for the case of 4 balls. And what this shows is you have 2 lines, and this corresponds to the 2 qubits. So the top line is the first qubit, the bottom line is the second qubit. And you can see, you've seen these gates. We have the Hadamard gate, we have the X gate, and there are some other special gates that do the other quantum effects. And you've already seen these ones. And the power is that, as you see at the beginning, we put the Hadamard gates on both of the qubits. So that means we're putting it now into superposition, which means that you're processing on all 4 numbers at the same time. And because you can now process at all 4 numbers at the same time, that makes it a lot faster. And then in the end, we actually make something called a measurement. So we end up actually getting classical information at the end, like bits 1, 1. But this is the power of quantum computing. So now that makes you question, what is the current state of quantum computing? I've talked about the applications, I've talked a little bit about how it works, but what can you do with it? So one of the most common questions I get asked when I'm saying I'm working on quantum computing is, when will we have quantum computers? What is your estimate? And my response is, now. We actually have quantum computers. They exist. And that's really exciting, because a few years ago, that wasn't the case. And so a researcher like myself, I can actually run quantum algorithms on a real quantum computer. So then you may ask, can you program a quantum computer? Yes, you can. You can program a quantum computer using quantum gates, such as the one I've shown you. So actually, since this is the Java keynote, let's look how you would do that in Java. So there are a bunch of quantum computing APIs that people have built. And this one is called Strange, and it's a quantum computing API for Java. And actually, I believe the creator of this is watching this on live stream, so hi. But let's see some of the code. And this is taken, and he's actually written a book on quantum computing and Java, and these are some samples taken from the book. So first of all, we're just creating a quantum circuit method. Now, in this case, this is like the syntax of the code, but to basically put it, we're creating a simulator. Now, what do I mean by simulator? Well, the thing is, as I said, quantum computers, underneath the hood, it's all vectors and matrices. So you can actually run a quantum algorithm on a classical computer. And then you may say, well, what's the point of the quantum computer? Well, it would just be a lot slower on a classical computer. That's why we need the quantum computer. But you can simulate it. So here we're creating the simulator. And there are other quantum programming languages that actually let you run it on the real quantum computing hardware. And so then we create a program. So we're just specifying, in this case, 1. And this is the number of qubits. So we have 1 qubit. Then a program is consisting of steps. As you saw in Grover's algorithm, there were the steps of the gates. So we're creating the step. And then we're going to add the gate. We're going to add the Hadamard gate. Remember, that puts our qubit into superposition. And we're applying it on the 0th qubit, which is just the only qubit we have. And then we just basically add the step to the program, and we get our result by running it on the simulator. So you can see that it's actually pretty simple to write code on a quantum computer. Now, the next question I get asked is, how do we build a quantum computer? Well, in order to understand that, we'd have to understand how we build on normal computers. Computers are made up of transistors, which act as the zeros and ones by blocking and allowing the flow of electrons. But it actually didn't used to always be that way. They actually used to use vacuum tubes to act as zeros and ones in the old days. But transistors ended up being more scalable, easier to use, and cheaper. So that's why we use them today, and it's taken off. But I bring this analogy because just as there were different ways to build a computer back in the early days, there's actually different ways to build a quantum computer right now. And here are some methods. So you can use superconductors. And the difference in quantum computing and computers is that when you have your bit, instead of just being 1 and 0, it also needs to be able to be in a superposition. And actually also needs to have the other quantum effects. And so all these substrates, we call them, can do all of these things, like put in a superposition and other quantum effects. So we can use superconductors, we can use trapped ions, which are atoms with a net electric charge confined into a space. We can use photons, which is basically light. And you can even use diamonds. And so you can see that there's a lot of interesting ways to build a quantum computer. And right now, the way people are trying to figure out which is the equivalent of the transistor, we're not quite sure yet. But I would say one of the most popular ways is superconductors. A lot of the big companies are working on that. But who knows if that's the equivalent of the transistor or something else. And so actually, I'm curious what you guys think. How many physical quantum bits do you think we have now on a real quantum computer? Let's see. Okay, interesting. All right, so you guys, okay. It's a good range in the middle, I guess. So the correct answer is, it's around 50 to 100 quantum bits. So as you can see, that's something, but it's not like a million, right? And now the answer goes up. But that's how many physical quantum bits we currently have on quantum computing hardware. So you may ask, well, why can't we just build millions of quantum bits on our quantum computers? Well, you could think one of the big challenges is that it's hard to keep the quantum effects. Just like when I'm spinning this donut, eventually it sort of stops spinning, and it loses its spinning. And it's just the same in a quantum computer. The qubits, they eventually lose their superposition. They eventually lose their quantum effects because it's so hard to control them and isolate them from everything else that's happening. And it's even harder when you have multiple qubits together. So it's a real challenge to build a quantum computer because you have to control these atomic particles and make them have all these quantum effects. But despite that, it's really amazing that we've already been able to build a quantum computer. So our current state is around a 50-qubit quantum computer. Now, what is the ultimate goal? The ultimate goal is to get to something called a large-scale quantum computer. This is one with millions of qubits. And as you can see, we're a bit far out. But the reason why we want to get to a large-scale quantum computer is because that is the one that could break your encryption, that could run Shor's algorithm, that could do Grover's search, that could revolutionize a lot of industries because that could unlock a lot of potential problems. We could do a lot of things with a large-scale quantum computer. But in the meantime, that doesn't mean that we can't do interesting things with the quantum computer. There are a lot of intermediate goals. And actually, one of the most immediate intermediate goals is something called quantum advantage. And the idea is that the current quantum computing hardware we have could solve a problem significantly faster than the best classical computers, supercomputers. And in fact, companies right now are working on this problem. They'll take an algorithm, they'll run it on a real quantum computer, and then they'll compare it to the best supercomputers in the world, and they'll see whether the quantum computer is faster. And people think maybe that this could happen in the next few months, if not maybe next couple of years. So this would be pretty exciting. And this could have a potential impact on a lot of industries. So what are people working on, and what else do we need to do in quantum computing? Well, I came up with an acronym called MATHS. So I'm from the UK, so we say maths instead of math in the US. But here is what it means. So M is milestone. So we need to outperform the best classical hardware running the best classical algorithms for a particular problem. This is the milestone of quantum advantage, because this shows that a quantum computer can actually do something that a classical computer, even the best supercomputers, cannot do. And hopefully we could reach this milestone soon. A is applications. We need to continue to create algorithms for useful applications for quantum computers. And in fact, a lot of companies are doing this. There are a lot of quantum computing startups that are working with big companies, and they're asking them, what are the hardest problems you have? And they're figuring out, could a quantum computer help solve that hard problem? T is theory. We need to continue looking at the theoretical basis, the underlying mathematics, and find more problems that are hard to do classically, but easy to do quantumly. H is hardware. We need to continue to increase the number of qubits, but also reduce the error in the quantum gates and qubits. As I mentioned, the error comes about when the qubit loses its superposition and other quantum effects. So it's not just the number of qubits that counts, but also the quality of the qubits. How long can they stay in superposition and maintain their quantum effects? So we need to continue to doing this in the hardware. And S is shift. We need to shift our mindset from the classical realm to the quantum realm. And there's a lot of interesting things that have been done around this, a lot of educational materials. There's a lot of quantum computing hackathons that popped up. In fact, Peter Shor himself, who invented Shor's algorithm, has a paper where he talks about why he thinks there haven't been as many quantum algorithms, because we're not familiar with quantum, and we don't know how to build these quantum algorithms. But there's a lot of exciting ways to educate people about this. And in fact, I started a quantum computing club at Stanford, and we've had workshops where hundreds of students have come to learn about quantum programming. And so we really need to develop the next developers for quantum computers. And so you've seen that on quantum computers, we could solve certain types of problems significantly faster. It could help us understand nature, which could help us in medicine and potentially artificial intelligence. I think there are two future states of the universe. One with a large-scale quantum computer, the one with millions of qubits, and one without a large-scale quantum computer. And right now, we're in a superposition of both. But paradoxically, as researchers, our goal is to break that superposition so that one day we'll have a quantum future. Thank you.
Thank you so much, Jessica. I really appreciate the way you both make it sound really simple, and yet you still blow our minds with the complexity, the possibilities, and some of the implications. Let's give her another hand, folks. Okay, this topic was a great reminder that we're working in a field which is continually changing in ways that we can't always foresee. Java is a technology that has stood the test of time in many ways, thanks to the guiding principles you see here, like ease of use, security, platform independence, and reliability. But the way that Java was delivered in its infancy, with large monolithic releases coming every few years and disrupting the entire industry, started to display its downsides as the world began to embrace more rapid cycles of change. We wanted to be more nimble, to get new features to developers more quickly, to be able to adjust course where warranted in the face of a dynamic world of new requirements. And so a couple of years ago, we announced our intention to move to the rapid cadence feature releases for Java, replacing the old major releases with smaller increments of gradual evolution every 6 months. Now, 3 of these releases have been delivered since then, and the 4th is imminent. We're proud to announce Java 13 with general availability starting tomorrow. Now, all right. Now, you'll hear a lot more about Java 13 later in today's keynote and also throughout the conference. Okay, so many folks were excited about the faster cadence. Many folks were apprehensive about the faster cadence. And there are a lot of people who were actually both. So this morning, we're going to hear from some of those folks about how it's gone for them. And actually, some of the most apprehensive people were those on my team at Oracle working on Java. They were used to the old model. It was familiar. They knew how it worked. They knew the good. They knew the not so good. And when we floated the idea of 6-month releases, they really thought I was crazy. It will never work, they said, because the Java community process through which the Java platform evolves, it just takes too long. This process requires that there be a specification, a reference implementation, and a testing kit which certifies that an implementation of Java is compatible. And this discipline meant more work that could be a challenge to faster releases. But it also provides a key to successfully ensuring compatibility while moving faster. I had faith that, like us, many in the JCP Executive Committee wanted to see faster and more gradual evolution of Java. So I went and spoke with them about it. And here to discuss how that went, I'm pleased to welcome to the stage 2 members of the Executive Committee, Gil from Azul and Bruno from SuJava. Hi, guys, welcome. In case anyone wonders, Bruno is from Brazil. Woohoo! Okay, Gil and Bruno, welcome to Code One. First of all, let me congratulate you and all of the JCP Executive Committee and members on our 20th anniversary.
I'm feeling very young right now, man.
There you go. So, Gil, what did you think when we suggested the rapid release cadence for Java?
Well, you mentioned apprehensive and excited, both. I think we were very skeptical, but the proof is in the middle. We just came off of 6.5 years between releases and just started settling in about 2 years, and that seemed challenging. A jump to 6 months seemed like a huge jump. And while the benefits were obvious and what you could do if it could be done was certainly something we wanted to go see. We had things like, just at the JCP EC, the shortest we've ever done a spec process through was 10 months before that. So, yeah.
Yeah, so, let me make inspired by Jessica, let me make an impromptu experiment here. So who here has, in your project today, you have an open source tool or an open source framework or an open source library? Okay, pretty much lots of people, right? Everyone, right? So now, who here works on a company or a project where you have stability requirements, and then that sometimes even prevents you from updating things for the newest and greatest release? Who had that? Okay, a lot of people, right? So that's exactly the same struggle that we had at the JCP. How do we do, the fast open source model at the same time that we guarantee the stability that we have that's so important for Java? So, and we have to remember that when the JCP was first defined, open source was defined that same year, right? So of course Java is not open source. There's OpenJDK didn't exist yet, and so we had to, to move to the fast cadence process, we had to take a very critical look at what we were doing at the JCP. And so we removed everything that prevented us from going to the open source friendly early release often model. But at the same time, we kept and we improved on everything that guaranteed the stability and the long-term release of the specification that's so important for the Java community.
Okay, great. So you mentioned OpenJDK and the JCP. I think some people in the audience might be kind of unclear on what the difference or what the boundary is there.
Yeah, so actually the boundaries are very, very clear, right? Innovation happens in open source. So innovation happens on OpenJDK. Open source is a great way to innovate, to collaborate, to solve new problems. But at the same time, we need to guarantee the long-term specifications, right? So companies like Azure and Oracle, they're here on stage, but so many others can compete in offering great products for their customers, right? And for that, we need compatibility, we need stability, and the JCP was made for doing that.
Okay, and how does that work out, Gil?
Well, I think it's worked out great. I kind of think from the quantum computing talk we just had, we had somewhat of a superposition of roles here in OpenJDK. We have, in the JCP, we have the reference implementation, the specification, and the TCK itself that come together. And in OpenJDK, we developed the reference implementation. We actually matured the specification. And then in the JCP, that all comes together, specified and solidified. But it's that result of an actual specification with a way to verify that it works that gives all the implementations, reference or otherwise, downstream from OpenJDK or not, the ability to all work in exactly the same way. The reason the Java ecosystem has such a rich set of code and libraries out there, the reason Maven Central works on all the different JDKs out there is because we do this work, because the specification is specific, and because the TCK lets us verify that all these implementations really will run the same way. So while there be differences on platforms and speed or features or something else, the code runs exactly the same way on all the things of the same version, whether it's a commercial implementation or a free community one, both of which we make. So I think that the OpenJDK place is where we all come together to develop this. The JCP is where we put that bar where we have a mature, this is exactly what it is every release, and it's now happening every 6 months. And then we have all these implementations, lots of them are based on OpenJDK, some are not, that actually are available for all of you to use under all kinds of ways, including a lot of free ones.
Okay, great. Thank you both for joining us.
Okay.
All right?
Thank you very much.
Thank you, Gil. Cheers.
Thanks, everyone.
Thanks all.
Thank you.
So the simplifications that we made to the process gave us great confidence that Java could evolve while retaining strong compatibility. But it still needed to be tried out in real life. Next, we're going to hear from a couple of developers who have been doing exactly that. Can we roll the video, please?
Hi, I'm Nikolai Parlok. I'm a Java developer, trainer on all things Java 8 to 13, and author of Manning's The Java Module System. I'm at Diese Informationssysteme right now, a German software development company for whom I migrated a larger project from Java 8 to 9 and then eventually to 11. I want to tell you a little bit about that. The project has about 1.5 million lines of code, split across roughly 450 Maven modules. It is now 20 years old, and as you would expect, it has a few dusty corners and dependencies. Speaking of dependencies, including the transitive ones, it has about 100. I guess you're not surprised to hear that the migration to Java 9 was not trivial. Some of the work was just cleaning up technical debt, which on its own already improved the codebase, but more was spent identifying problems in dependencies. Mind you, this was over the summer of 2017, when Java 9 was still in early access and projects didn't yet officially support it. Now, 2 years later, thanks to the work of the amazing maintainers in Java's open source community, most widely used libraries and frameworks just work flawlessly on Java 9 and later. And that's great news for you. Chances are, all you have to do to upgrade to Java 13 is to update some of your dependencies and tools. And I know, that's easier said than done, but if we did it, you can do it too. So if you're still on Java 8, go to your vendor of choice, download JDK 13, and just run your build on it. You may be surprised by how little else you have to do. Why you'd want to upgrade? Licensing and support aside, Java after 8 has a lot to offer. I'm obviously a big fan of the module system, but even ignoring that, there are tons of seemingly small changes that amount to quite a lot. var, switch expressions, text blocks, better performance, new garbage collectors, new and many improved APIs. We really enjoy working with the new releases, and as great as 8 is, we never looked back. If that didn't persuade you, let me quote Boris Terzic, a good friend of mine and head of development here at Dizzy. I would do anything to get to value types, he said. And with an eye on Project Loom, I want to add, and to fibers. There are so many great improvements in the work. It would be a shame to miss out on them just because upgrading from Java 8 requires a few days' work.
Hi there, my name is Raphael Winterhalter and I'm a software consultant at Sienta in Oslo, Norway. Some of you might know the work I'm doing in open source. For example, I'm part of the team developing Mockito, but mainly I work on ByteBuddy, what is a code generation library that is used by many other libraries and frameworks in the Java ecosystem. I understand that some of you might think that because of libraries like mine who need to adopt to every new Java release, it is the safest to wait until the Java ecosystem has moved forward to take a new Java version into use. But let me assure you, in the last 7 years, ByteBuddy has always supported the latest version of Java, and I don't really see why this will change in the future. So all you need to do to make use of Java 13 and any other Java version that comes out in the future is to keep your dependencies up to date, which, by the way, is something you should do anyways, because only the latest version will include all the bug fixes and performance fixes that we are releasing all of the time. So please just go ahead and try out the newest versions, because in my CI builds, I can really see what Java 13 has improved over since Java 8 and earlier versions, because things go so much more faster and they are more stable. So I'm sure the same will happen for your production systems. Just go ahead and try it out. Enjoy the rest of the conference, but once you're home, please go and dust off your production servers, throw in Java 13 and see what it does for you. I'm sure you will be positively surprised by the results. Thank you.
So one question I get a lot is, the JDK is careful about evolution, and well-maintained libraries are keeping up. But what about the tools that I rely upon? We know that availability and choice of great tools is super important. And we want to ensure that the tools vendors are taking part in the ongoing innovation of Java. Our next guest can speak to this very specifically. Please help me welcome Chris from New Relic, Brian from AppDynamics, and Mala from JetBrains. Okay, Chris, why don't you tell us a little bit about New Relic's tools and your experience with the rapid releases?
Yeah, so New Relic is a application monitoring company that monitors a bunch of Java applications, other platforms as well, to provide complete observability of your system so you understand how those systems work. And so the main thing to take away here is that New Relic monitors over 1 million Java services around the world. And so we've got a lot of insight on how people use Java. And we found that Java developers update quickly. They're using the latest libraries and frameworks, as well as the latest JDK. So that's one of the reasons that New Relic works hard to be compatible with the JDK releases as they come out. And that includes for Java 13. We will be compatible with Java 13 this month.
All right, thanks. So, Brian, why don't you tell us a little bit about AppDynamics and how you've prepared for the rapid release cadence?
Sure. Today, AppDynamics is used by thousands of organizations to monitor literally billions of classes that are in production. Many of these applications are the kinds you use online every day to book travel, to do your online banking, whatever it is online, because we monitor the performance of the experience that those customers are having. Given that these systems are so important and critical to those customers, we have spent a lot of time this past year investing in our CI/CD pipeline so that we can download the latest versions of the Java JDK, run a whole bank of tests against that, so we have automated testing, so we can identify issues before our customers see those issues in their production. And it sounds like today, with 13 up, we've got our work to kick that CD pipeline into place again. So.
There you go. And you know, just so you know, the early access builds of 14 are already available. So you have a lot of great stuff to do. OK, Mala, with multi-year releases in the past, sometimes it took months or even years for your favorite IDEs to support the new features. So how has JetBrains been approaching this, and what are you doing differently?
So at JetBrains, we have a 4-month release cycle, which really means that we have no problems with adapting to the release cadence of Java. A new version of Java is released, and we release a new version of IntelliJ IDEA with all the new language features. And we set a very high bar for ourselves in supporting the new language features. We're not only working with basic features like error highlighting or code completion, it's also about providing functionality like automatic migration to the new code constructs. And that's not all. We also update our existing set of inspections and coding assistance tools so they work really well with the new code features. And early support of new language features in IDE is important for the ecosystem on the whole. With the new features available to the developers, they can work on it, they can submit their feedback to Oracle, which is important for the preview language features. And that's not all. We are active participants in the design considerations of the new language features with Oracle and how it can affect the tooling.
Okay, Mala, that's great. If folks are interested in hearing more, where can they go?
So you can go and check out the session on tooling for IntelliJ IDEA platform plugins by Jan Sebron. And you can also come by our booth to see how our tools support the new language features and much more.
Okay. And same question for you, Brian.
Sure, yeah. Folks can stop by our booth. I think it's booth number 3100 and ask any questions you have.
Okay, excellent. Chris?
And the best way is to start at newrelic.com and go there to learn about how complete observability can help with your systems and understanding troubleshooting, performance analysis, et cetera. And from there, you can either request a demo or just download the software and try it out.
Okay, thank you all very much. At Oracle, we believe in an ecosystem of great tools for Java, not just things that we do, but we want to enable a large set of people to do these tools. So we welcome and we work with tools vendors as we're developing the JDK. Okay, so now we've heard from app developers, library developers, and tool developers about their experiences with the rapid release cadence. But sometimes there are situations where you have a system which is running and you just want it to keep going with updates for security, stability, and performance, but without any potential interruption by new features. A year ago, we introduced the Java SE subscription from Oracle in order to help customers with this situation. And we've had, I'm pleased to say, many thousands of customers who have signed up for this. Today, we have one of those customers with us to talk about his experience. Please help me welcome Kenny from Sabre. All right, welcome, Kenny. First of all, everyone in the audience may not be familiar with Sabre. Why don't you tell us a little bit about Sabre, and if you can also tell us, how you're using the Java SE subscription for your business.
Absolutely, thank you. Happy to be here today. Sabre is one of the leading travel technology providers today. We connect travel suppliers such as airlines and hotels and cars, rail crews, together with travel buyers in a comprehensive travel marketplace. Over the last several years, Sabre has been actively offloading applications off of the mainframe onto applications written in Java. And Java has proven to be a good platform for us. It has a rich set of libraries and frameworks and allows us to focus on our core competency. Java and its ubiquity also has proved to be a very good language for us because of the pool of talent from which we can recruit from. In a single minute in Sabre, thousands of shops are made for airfares and hotel rates and car rates. Thousands of passengers are boarded at the airport every day. Hundreds of bookings are made in the system. So when Sabre is not available, there's a whole lot of inconvenience. There will be aircraft that are grounded and won't be able to leave. There will be passengers that are stranded at the airport. As such, stability and security are extremely important for us in our business. The adoption of Java SE and the long-term support model allows us to innovate at the rate that matters to us in the travel space. And it also gives us the stability and security that we need to be PCI and GDPR compliant. And so we look forward to this partnership with Oracle to continue to be the best at what we do.
All right. Thank you very much, Kenny.
Thank you.
So, yep. I'd like to thank Kenny and also all of the other subscribers we have, because your subscription helps support the team that's leading the innovation of Java. Now, with nearly 25 years behind us, many generations have actually grown up with Java. But for technology to endure the test of time, it needs to remain attractive to future generations. We're investing today so Java can remain vibrant for another 25 years and more. And we can all encourage a new generation of developers to discover Java. My next guest is a great example. She has a young adult novel coming out next week where Java plays a key part. Please help me welcome Amy Lucido. Okay, Amy, why don't you tell us about your book?
Yeah, so my book is called Emmy in the Key of Code, and it's a story about a 12-year-old girl named Emmy who comes from a family of musicians. Her mom's an opera singer, her dad's a pianist, but she feels like she's not actually good at music. So when she moves to San Francisco for her dad's job, she decides, I'm not taking music classes anymore, and she ends up taking a computer science class. What she doesn't expect is to fall in love with coding, and not only to fall in love with it, but to rediscover music through it. But what I think makes the book special is that it's a novel in verse, which means it's a novel, like a single story, but it's told in verse, so poetry. And as she learns to code, she starts to incorporate the if statements and while loops of Java into the poetry. So poetry becomes sort of a literary device, but also the idea is a kid would read it for the story and accidentally learn a little bit of Java at the same time.
Okay, so you could have chosen anything. Why did you choose Java?
So first and foremost, I'm a Java developer. I've been working in Java at every company I've worked at, Uber, Google, Facebook. But even more than that, Java was the language that I learned to code in. I was a junior in high school taking AP Computer Science. And I'll never forget this. I had a computer science teacher who the very first day of class, we were making our first Hello World program. And obviously, the thing that every new Java developer has to do when they make a program is type public static void main string bracket bracket args. And as a student, obviously, I had no idea what this meant. And my teacher anticipated this. And he said, you're not going to know what this means, so just memorize it like a song. And so he rapped it. He goes, public static void main string bracket bracket args. And that stuck with me. Like, I still remember, this is a decade ago. And so when I started writing this book about a girl learning how to code, how, especially incorporating the music aspect of it, how could I not write it in Java?
Okay, so I imagine that, like me, a lot of folks out there are wondering how they can get a hold of a copy.
Well, that is a great question. It is available wherever books are sold, so Amazon, Target, Barnes & Noble, all the above, your local library or local independent bookstore. But as an author, independent bookstores are our lifeblood, particularly for those of you who live in San Francisco. There's one in particular that I am partnering with throughout this whole process. It's called The Booksmith, and it's up in the Haight. And I'm doing a launch party there next week on September 24th with my publisher, who's, for any of you who have children at home, you might recognize the name Kwame Alexander. He wrote a book called The Crossover, which is a very famous novel in verse for children. And so he's actually coming on Tuesday to interview me at the Booksmith. And so if you buy a book, not only can you come to the launch party, but also, or if you're not, if you're not local, we can ship it to you and I'll sign it, which you can't get through Amazon.
All right, thank you so much.
Thank you so much.
Okay, we've tried to make the QR codes large, so you can just take out your phone and go directly there and pre-order. All right. So this morning, we heard from a range of folks who are getting value from Java using the latest features, as well as those who are enjoying the convenience of long-term support. So far, we've been speaking with people who are mostly using Java, and now it's time to hear from one of the stewards who makes Java. So please help me welcome the Java language architect, Brian Getz.
So I'd like to start by recapping where we were last year at this time. So last year this time, we had just shipped Java 11. And this was the second release that we had done under the rapid release cadence, and it was the first long-term support release. Since last year, we've continued to deliver new releases like clockwork. Now, as George said, a lot of people, including, quite honestly, us, were pretty skeptical at first about the rapid release cadence. It seemed inconceivable that we could turn a ship as big as Java that quickly. There were even fears that Java 10 and Java 11 might have no features at all. And looking backwards, it's really hard to overstate what a significant change the rapid release cadence has been. There are, of course, the obvious benefits that we can deliver value more often, and you don't have to wait as long for any particular feature to come out. But what's really been significant is how it's brought out this fundamental change about how we design and plan and deliver new features. So by lowering the cost of a feature missing the boat, missing by 6 months is a whole different story than missing by several years. It's drastically reduced the degree of release management overhead that we have to undertake, internally, and that in turn lets us spend more of our energy on designing and building features and less energy on managing releases. And at the same time, having more release vehicles has encouraged us to learn how to break down complex features into smaller ones that we can deliver in phases. And in addition to delivering value faster, this also can reduce the amount of time that one feature might spend blocked on another. And the result, which has sort of been an unexpected one, is that our feature pipeline has become richer than it's ever been in the past. The whole thing has been one big virtuous circle. So a lot of you are still probably using Java 8. So at the risk of repeating a little bit of old news, I want to do a quick walkthrough of what's gone on in the past few releases. So these are the major features that were added in JDK 10. It's not an exhaustive list. This is just those that were big enough to merit their own feature plan. And in addition to these, every release has hundreds of smaller enhancements and bug fixes. So enhancements can come in any platform area. They can be language features like local variable type inference, commonly known as var. Or they might be library features, such as support for newer standards like Unicode. Or they might be runtime features. So in JDK 10, there were improvements to the garbage collector, and we released the application class data sharing tool, which allows class files to be pre-digested for faster startup, and we added experimental support for the Graal CE JIT compiler. JDK 11 similarly introduced features in every platform area. On the library side, for example, we saw a new HTTP client API, several new crypto algorithms, and support for several standards, TLS 1.3 and Unicode 10. And on the runtime side, we saw a significant new feature, Java Flight Recorder, which is a low overhead monitoring tool that records events about what the JVM is doing into a circular buffer, kind of like the flight data recorder on an airplane. And when something interesting happens, say some kind of exception is thrown, then you're able to see what was happening in the JVM in the moments right before that happened. And because it's so low overhead, you can run it in production all the time, always on, and this gives you better insight and visibility into what's happening in your application, and faster recovery time when something goes wrong. In 11, we also released the Z garbage collector, which is a new garbage collector, low pause collector, and can support very large heaps up to many terabytes. Both of these features, as well as application class data sharing, which we released in 10, had previously been part of Oracle's commercial Java SE Advanced product. As of 11, Oracle has open sourced all of them and contributed them to OpenJDK. And the improvements keep coming. In JDK 12, there were a number of improvements to startup and garbage collection, as well as a new language feature, switch expressions, which I'll talk about in a little bit. And similarly, in 13, there were more improvements to startup and garbage collection. There was a complete re-implementation of the socket API. It's only been 20 some odd years. And another new language feature, text blocks. So one of the adjustments that we all have to make in this new world is to recalibrate our expectations about what constitutes something worth upgrading for. In the old world, when we had big releases every few years, and those big releases tend to have big features like generics or lambdas, there was already plenty of motivation to upgrade. Now, the reality is we're not going to be seeing a lot of those big features in the future. And that's not because we're not innovating. It's because those big features are going to get broken up into smaller features and delivered in phases. So there's just as much innovation going on, perhaps more. It's just going to be spread out over a larger number of smaller deliveries. And so we need to adjust our sense of what constitutes something new. Now, as developers, we have a tendency to pay most attention to language and library features, which makes sense because we look at code all day. Now, language improvements make us more productive, but we shouldn't forget about runtime features as well. Improvements to the runtime allow us to take existing code and just run them on a new version of the platform and pick up benefits like better performance, better reliability, better observability. One of the key value propositions of the Java platform is you can nearly always just run old code on a new runtime. So to take a look at some of the benefits that you'll get by, say, upgrading to Java 13, let's bring out Michael Vidstead. So most of us only notice the runtime, frankly, when it misbehaves, which I guess is kind of a good thing. But the flip side of that is it's really easy to take improvements in these areas a bit for granted.
Yeah, that's pretty much the story of my life. So if the garbage collector and the JIT compiler and all of those subsystems in the runtime, when they do their job well and perform well, nobody will notice them. And that's pretty much the definitions of success for us in the end, right? But achieving that success, that doesn't happen by accident. It's something we work really hard on. Now, everybody agrees that performance is really important, but not everybody agrees on exactly what performance is. So in some cases, it's startup time. In other cases, it's throughput, or it's responsiveness. The list goes on, right? Basically, what that means for us is that we need to sweat all those different types of performance and make sure that all of them work really well. But let's start from the beginning. Let's start with program startup. So before any code can run, the VM needs to do a bunch of work. So it needs to load classes, initialize VM data structures, and so on. And all of that work shows up at startup time in one way or another. Now, a lot of that work is also really an investment into getting better performance later. But of course, that investment really only pays off if your application is going to run for long enough. So to give you an example of the type of improvements we've done to startup time over the last few years and releases, I'm going to show you a chart here with the startup time for a simple, sort of minimal Hello World application, and all the way from JDK 8 to 13.
So I certainly like the trend, but something happened there between 8 and 9. What was that?
Yeah, that's right. So JDK 9 is the first release in which we included the module system. And as part of modules, we do some work up front, one of those investments into getting better performance later. In particular, what we do is to validate the module graph. And basically what that allows us to do is load classes much more efficiently later. So it's a good investment, right? But it did set us back a bit on the startup time side, as you can see. Now, through hard work and over a few releases, we got it down. So now it's actually below where we were in JDK 8. So we're down to 40 milliseconds or so, I believe.
Well, that's great. And I'm sure you didn't mean to pick on modules.
No, that's right. This is typically something that happens for all the big features we have. So let's take lambdas as another example. So lambdas are awesome, right? They make us as Java developers much more productive. But the very first lambda that gets executed does have an initialization sort of startup overhead associated with it. If we take a look at this a similar sort of Hello World style application, this time there's a lambda in the main method body, we can see that back in the JDK 8 days, the overhead of that first lambda was, I'm going to say, 80 milliseconds ballpark.
And I think I wrote that code, didn't I?
Yeah, you did, Brian. And guess who had to go in and clean up after you, huh? But we did. So through hard work, over a few releases, we got it down. So now it's only adding a tiny bit, maybe, let's say, 6 milliseconds or so.
OK, so I don't have to feel that guilty.
No, that's right. The lambdas are awesome in the end, as I mentioned. And so let me give you one more example of startup time improvements. So in this case, I'm going to show you the effects of running with application class data sharing that you mentioned earlier. So this is showing the Micronaut microservice framework and the startup all the way from 8 to 14 in this case. The blue bars here are the out-of-the-box startup time, and the orange ones are using application class data sharing.
So how exactly is it that AppCDS improves startup?
Good question. So as I mentioned earlier, before any code can run, the VM needs to do a bunch of stuff, right? And among them, load classes. Now, it turns out that the on-disk representation of a class file does not exactly fit well at runtime. So the VM needs something more efficient. And basically what it does as part of loading classes is transform the data and put it into something that makes more sense, right? What class data sharing allows us to do is to do that transformation work ahead of time. So using a build time tool, you can create something that looks very much like a shared library, and then the VM can simply map that library into memory at startup.
But we didn't start with class data sharing in 11, right? It's been around for a long time.
No, that's right. So already back actually in JDK 5, we had something called class data sharing. And basically at the time, though, it was limited to system classes. So basically think Java lang string. What we've done over time is to expand on the functionality. And with application class data sharing, which, by the way, used to be a proprietary feature that we opened up in JDK 11, we're now giving users the access to that powerful functionality. And you can now store class application or user classes in the same shared library as well. If you want to know, by the way, more about all of this or the improvements we've done to startup time over the last few years, you can go to Klaus Reddestad's session later in the week. He's going to talk about all this stuff that I mentioned and then some more in detail.
So I certainly like how people can get this big improvement just by upgrading to the latest JDK, and certainly startup has improved dramatically. If that's not good enough, is there more that people can do to improve startup?
So if you have even more stringent requirements on startup time, you may be interested in looking into the native image tool from GraalVM. So basically what that tool does is to compile your Java applications down to native code. There is slightly more work involved in getting it, but the startup performance is truly dramatic. So there's a session later this week from Christian Wimmer on that exact topic. So if you're interested in knowing more, you can attend that.
Very cool.
So much like with startup time, we are improving on performance in other areas as well, and garbage collection is one of them. So we have to invest in this area because over time things change, right? So hardware evolves and so do expectations. So when I started working on Java, which is a long time ago now, big heaps were counted in, say, hundreds of megabytes or so. Now when we talk about big heaps, we're more thinking in terms of terabytes, and the similar sort of evolution has happened on the number of cores in the CPU.
It's like one big game of catch-up, isn't it?
Oh yeah, no, we constantly need to be on top of this. And so to give you an example of the improvements we've done on that side, I'm going to show you an industry standard benchmark here, and it's showing the performance of the G1 collector. G1 is the default garbage collector in the JDK since of JDK 9. And this benchmark here is showing two sets of bars. So the blue ones are throughput, and the orange ones are responsiveness, roughly. And as you can see here, there are basically improvements in every release. And if you look at the difference between JDK 8 to 14, you can see that on the throughput side, the blue bars, we're seeing roughly 10% improvement or so. But more impressively, looking at the responsiveness side of things, we're looking at 65%. So a lot of good work has gone in there, and we're continuously improving on this as well.
Yeah, so clearly there's been a lot of investment in G1, but there's also been investment in a new collector too, the one with the funny name.
Yeah, yes, that's the Z garbage collector, or ZGC for short. ZGC also used to be one of those proprietary features that we open sourced in JDK 11. And it is a low latency garbage collector where we're looking at millisecond or so pause times, even for those really big terabyte heaps I mentioned earlier. So to show you a bit more of where we are with that today, I'm going to show you the pause time distribution for that same benchmark. And in this case, we're seeing the average, percentile, and max pause times for 3 different garbage collectors. It's parallel, which is sort of throughput-oriented. It's G1 that I just mentioned, and the new ZGC collector.
So it looks like the pause times for the Z garbage collector are basically 0. That's what Z stands for?
Yeah, it's not exactly 0. So I'm going to help you here by magnifying that part a bit. And I will also taken the liberty of multiplying the pause times by 10, just to make sure that they sort of show up on the radar here, right? And basically what you can see here is that the average pause time for ZGC is actually less than a millisecond, and even the max pause time is less than 2.
All right, so that's incredible, but there isn't a free lunch here, right? If we're getting these amazing pause times, we must be paying for it somewhere else.
That's right. So in the end, as always, this does depend on your workload. What we're typically seeing is that G1 has slightly better throughput, so maybe a few percent or so, and also for smaller heaps, so in the gigabyte range or so, G1 is likely to do slightly better, let's say. Unfortunately, we don't have one GC to rule them all yet, but it's something we're working on, so to speak. This next chart shows that slightly more in detail. So again, same workload. If we start by looking at the responsiveness metrics, so the orange bars, as the pause times become more predictable, we see that the responsiveness metric goes up. But the cost sort of comes on the throughput side. So in this specific case, the throughput overhead for CGC is maybe 2–3% or so, and that's sort of the cost of getting that more predictable runtime. Now, in the end, this does depend on your workload, and for many applications, this may well be a sensible trade-off, that 2 to 3% cost, but it all depends on your performance goals.
All right, great. Thank you very much, Michael.
Thank you.
So Michael has a talk tomorrow where he's going to go into much more detail on the progress in the G1 and Z garbage collectors. So if you're interested in garbage collection, come see Michael's talk tomorrow. And as you can see, we've invested a great deal into maintaining and improving the runtime. And like I've said several times, these improvements are available to existing applications just by updating the JDK, usually with no change to your code. So now I want to take a peek into the development pipeline. So advanced work in OpenJDK goes on in projects that have fanciful names like Valhalla or Loom, and they represent long-term investments. Many of them have made significant progress in the last year. So I'm going to do a quick overview of the landscape, and then I'm going to drill into some specific features from Amber and a little bit of a demonstration on Valhalla. So Project Amber is our umbrella project for what we call right-sizing language ceremony, and this is where most of the smaller, more productivity-oriented language features have come from. Project Valhalla is about aligning the Java object model with the performance characteristics of modern hardware. This one in particular has been a long road. We've probably been working on this for about 5 years now, but in the last year it's really started to bear fruit. And there's a very nice talk this afternoon from Sergey Kuchenko on Oracle's performance team about the motivations for Project Valhalla and why you might be interested. Project Panama is aimed at rebooting the interaction between Java code and native code and data in the native heap, and has also made huge progress in the last year. And we're actually hoping to see the first, a preview version of the first deliverable from Panama in the next year, which is going to be a new API for efficiently accessing off-heap memory. And we hope this is going to be a much-needed replacement for direct byte buffer. Panama is also looking at how vector operations that are supported by modern processors can be exposed directly up into the programming model. And there's, again, a talk this afternoon by Vladimir Ivanov on the vector API that does just this. And Project Loom is about eliminating the scalability bottleneck of threads by implementing continuations in the JVM and fibers in the JDK. Now, I could talk for hours on any of these projects, but I only have a few minutes left, so I'm going to take a quick peek into 2 of them, Amber and Valhalla. So we've already seen significant output from Project Amber. This brought us local type inference in Java 10, switch expressions in Java 12, and text blocks in Java 13. And it's poised to deliver several new features in the coming year, records, sealed types, and the first installment of pattern matching. Now, none of these are going to be as big or earth-shaking as Lambdas were, but that's OK. They're useful features that address real pain points that developers experience every day. So let's take a closer look at the Amber features that went into 12 and 13. Switch expressions are a refinement to the switch statement to allow it to be used as, well, an expression. And if you look at typical switch statements in real code, what you'll see is most of them kind of wanted to be expressions anyway. They compute some value based on a multi-way conditional, stick that value in a variable, and then use that variable later. But in order to express it as a statement, we end up having to do it in this roundabout and therefore error-prone way. And if we could express them directly as expressions, instead of simulating them with statements, we would make our code more clear and leave fewer places for bugs to hide. So on the screen here, I have an example of a typical switch statement that kind of wishes it was an expression. And we all know the annoyances of this. You have to say break on every case, and if you forget that, that's a silly bug. And you have to have this do-nothing default, even though you're switching over an enum and you've covered all the values anyway. So I'm going to show what this looks like, converting this to a switch expression, and I'm going to do it in the IDE because IntelliJ already has great support for switch expressions, including refactoring. So if I ask my IDE, if I hover over the switch statement, it's going to suggest, oh, this switch statement could be made into an expression. Do you want to do that? And I say yes. And then I can go ahead and clean up the rest of the code, like inline away the temporary that's no longer useful. And the IDE also suggests maybe you want to get rid of this default clause because it doesn't do anything. And the result is something that's not only more concise, which we like, but it's also much closer probably to what we had in mind when we sat down to write this code in the first place. Another kind of interesting thing about switch expressions is where the feature came from. This was originally part of a larger feature, pattern matching, and we were able to extract this out as a standalone feature and deliver it earlier while we continued to work on pattern matching. So this is another example of how the rapid release cadence continues to deliver value and enables us to deliver value faster. So another small feature, but highly requested feature we added in 13 was text blocks, also known as multi-line strings. So it's not a particularly sophisticated feature, but it is something that makes a big difference in everyday code. So let's say you want to express this block of HTML as a string in your Java code. So the way you do it today is you have to mangle the strings by inserting escape sequences and wrap them as individual single-line strings and then concatenate them together. And this kind of manual mangling is, it's irritating, it's error-prone, and it makes the resulting code harder to read. It would be nice if we could have just cut and pasted that bit of HTML right into our Java editor. So here we see what the result is of replacing the traditional string literal with a text block. And a text block is a lot like a traditional string literal. It can use the same set of escape sequences. It just uses a different delimiter, and it's allowed to span multiple lines. Now, when we move to a multi-line format for our string, we kind of have a dilemma. On the one hand, we want to indent the text block with our code so our code looks good. On the other hand, we probably didn't want that extra white space in the body of our string itself. And so we use a heuristic to determine which indentation is essential and which is accidental, and then we trim off the accidental indentation at compile time. So in this, in this example, the gray dots show us where the indentation was deemed accidental. Under the old release model, there was a lot less motivation to do smaller features like this because it would take so long to deliver them, and they tended to get lost behind the bigger features. And frankly, when we were focused on big features like Lambda, it was, they tended to crowd out the attention that smaller features might have gotten. And so the rapid cadence has also had another hidden benefit, which is allow us to achieve a sort of more sensible mix of big and small features. Now, everything I've talked about so far is shipping now. You can use them by upgrading to Java 13, which is JAD this week. And so now let's take a quick peek into the near future. So every Java developer is familiar with the pain of declaring a domain class. We have to repeat ourselves over and over and over again with fields and constructors and accessors, equals, hash code, toString, all of that. So the root of this problem is that the class mechanism in Java is very general. It can model anything, but the modeling overhead for something simple like a domain class is really quite high. And the code that we have to write is fairly low-value code. Now, sometimes people resort to code generators to solve this problem, but I think that's just a Band-Aid. I mean, the real problem is that we've expressed things at the wrong level of abstraction. We want a way to say, this class is just a holder for its data and nothing more. And that's exactly what records do. It's a way to make the statement, I am just my data. And by making that statement, we give up something. We're giving up some flexibility over our API, but in return, we get a great deal of concision because the compiler understands what we mean. So when we say, this class is just its data, a point is just int x, int y, all that boilerplate code can go away, and we're left with a clear statement of what we mean. And the compiler automatically fills in fields and constructors and accessors and equals and hash code and toString and more. And if you want to refine those or add new members, you can, because it's just a class. So some of you may be thinking, gee, I think I saw this example last year. And that's true. And it's a good illustration that even though we can ship features every 6 months, it doesn't necessarily take only 6 months to develop a feature. Even a small, simple-looking language feature may take more than 6 months to develop. But the good news is records and their cousins, sealed types, have largely completed the design process and are being finalized for delivery. And we hope to ship those in the next year. Now, I know everybody will like the concision of records, and concision is one of the goals, but it's not the only goal, and it's not even the main goal. It's satisfying to eliminate repetition from our code, but more importantly, eliminating repetition eliminates places for bugs to hide. And it eliminates clutter that gets in the way of reading code and understanding what it does. And there's another hidden benefit to records as well, which is by reducing the overhead of declaring a new data abstraction, it reduces our incentive to be lazy and cut corners. We're more likely to do the right thing and end up with better code. OK, so if you're interested in more about what's going on in Project Amber, I've got a talk tomorrow at 11:30, and I'll go into much greater detail. And also, there is another talk on Wednesday by Stuart Marks about local variable type inference, was a feature that came out of Project Amber in Java 10. OK, so let's switch over to Project Valhalla, which is aimed at aligning the way Java lays out data in memory with the performance characteristics of modern hardware. Hardware has changed a tremendous amount in the last 30 years. 30 years ago, the cost of an arithmetic operation and the cost of memory fetch were about the same. They were a handful of clock cycles. Hardware has evolved a lot since then, and as it's evolved, arithmetic has gotten cheaper, and memory access has gotten more expensive. So nowadays, if you cache miss all the way out to main memory, that could cost you as much as 300 clock cycles, and we can issue multiple arithmetic operations on each clock cycle. And as a result, compute-intensive programs often spend a lot of their time waiting for data to operate on rather than doing useful work. So what does this have to do with Java? Well, in Java, almost everything is an object, and objects have identity. And as a result, the JVM generally has to represent objects as nodes in the heap. And those nodes have object headers. So a simple class like point, it has an object header, and an array of points is really an array of pointers to points. Now, this layout isn't ideal for a lot of reasons. It's not ideal from a memory utilization perspective, because we're spending a lot of memory on object headers and pointers. It's not ideal from a locality perspective. To operate on the data, you have to traverse a pointer, potentially incurring a cache miss. And it also makes more work for the allocator and the garbage collector. And even if you allocated all these points at the same time, so they were local in memory, if the garbage collector comes along and rearranges your heap, now all of a sudden your locality is all gone. Now, we like primitives because they get flattened into objects and arrays. But once we start using classes, we start to pay this abstraction penalty. Now, no reason to panic. Java is plenty fast. But we won't be satisfied until users don't feel like they have to choose between abstraction and performance. So Valhalla's answer to this problem is to make a deal with the programmer. The programmer says, I promise object identity is not significant in my program. And that means giving some things up, giving up mutability and layout polymorphism. And in return, the VM can reward us with a much better data layout, something like this, which gives us better density and better locality. So, all right, pretty picture. What's the point? Well, let's take a look at how this affects a real-world workload. So we pulled together a quick implementation of a Mandelbrot set visualizer. Mandelbrot set is defined on the complex plane, so first thing we need to write is a complex number class. And this is easy to do. It's a straightforward Java class. But we're in that situation now, like we were in the previous diagrams, where each complex number is a heap allocated entity. And the highlighted lines show where the allocation might happen. Similarly, if we look at the code for our Mandelbrot viewer, we're going to do some computation on those numbers. And again, there's a number of places where allocation might happen. And so while this program, what it wants to do is compute pretty pictures, it's also doing a fair amount of allocation, and that may be slowing us down. So let's go back to our complex class. We'll make a simple change. We'll say, let's make this an inline class. And then we'll look at the effect of doing that on our Mandelbrot viewer application. So we'll get out our popcorn, and we'll watch the pretty pictures. On the left, we have the traditional implementation. On the right, we have the Valhalla implementation. And what we see is the traditional version, once it gets going, gets on the order of 15 to 20 frames a second, and it's allocating something like 10, 11 megabytes a second. Whereas the Valhalla version is doing way less allocation, and the frame rate is nearly triple. So it was a one-word change to our program, 3x improvement in our frame rate. Now, part of the improvement came from doing less allocation. That's not the whole story. It also eliminates data indirections, which allows the CPU to spend more of its time computing useful values and less of its time waiting for data. So in the last year, Valhalla has made huge strides. There's a public early access release out there that's suitable for experimenting with high-performance data structures. And in the next year, we'll be working on how to surface this out in the language. So, OK, so that was some pretty quick capsule summaries of some pretty big projects. If you didn't follow all the details of that, don't worry. There's a bigger point here, and that is the feature pipeline is deep and rich, and we now have many more opportunities to deliver pieces of the story. So it's time to wrap up. I'd like to leave you with one last thought. This is a great time for Java. We're delivering faster, there's useful features in every version, and the pipeline for the future is better than it's ever been. As always, you can get the latest binaries at jdk.java.net. Have a great time at the conference. Thank you.